Well, let's have 10 dimensions, let's have 11, let's even have 26. Apart from let's have multiple universe, let's have multiple dimensions in the universe we have. And to act as though they can just do that, that's fine.
Yeah, but there is a problem with Einstein's 4 dimensions.
Oh, I will show you that there is a problem with the 4 dimensions.
Very good.
It's a different problem perhaps to the one you've got, but I've got a problem with 4 dimensions. But however, space, the only physical parameter that gives us a direct way of apprehending any part of the universe in any way through measurement is most definitely 3-dimensional. There's no point in denying it. Our space cannot be extended to 9 dimensions of space in one time. You can't make our space 9 dimensions. It breaks rules of algebra and physics that you can't break, like there's no cross product if you go any higher, and we know we've got cross products. We know from Fleming's left and right hand rules and lots of other things that we have cross products. Oh, sorry, that's what's... Right, and of course, many people have said how difficult it is to understand why is the world 3-dimensional. Well, we know exactly why 3 dimensions comes about. It's not difficult at all. It's been known for a long time. It's been known for 150 years why 3-dimensionality is special. And this is who discovered the reason why we have 3 dimensions. This is William Rowan Hamilton, trying to extend the 2-dimensional complex number system to explain 3-dimensional space. And the original complex number system was the vertical line and the horizontal line. The vertical line being the imaginary numbers and the horizontal line being the real numbers. And this is a sort of 2 dimensions. But it's not 2 dimensions as we understand it. The dimensions are different. Whereas when we have 2 and 3 dimensions, the dimensions are the same. And Hamilton tried to get a 3rd dimension that was imaginary. And it failed because there was no place for a product of the 2 imaginary dimensions. You just couldn't create one within the system. And eventually he said, we have to make it 3 imaginary dimensions and get rid of the real one off the axes. So we had 3 real imaginary dimensions, made them cyclic, ij equals k, ki equals j, and so on. And not able to show the real dimensions. Of course, the fact that you still had a real dimension, even if you couldn't show it, meant that in some way the 3-dimensional quaternions, as he called them, had to be part of a larger 4-dimensionality, and that's why we call them quaternions, not triennions. So you can't define the 3-imaginary without having the real one. And each of the 3 imaginary ones is like, itself is like complex number system with the real axis. Each of them is. Well, the one isn't like the other 3. It can't be totally absorbed into them. It's a broken relationship, like the original one we started out with, the complex numbers. That is a broken relationship. The 2 dimensions are the same thing. And of course, he found that quaternions were anti-commutative. In other words, ij equals minus ji equals k, and so on. And to show that, it's very easy. If I do ij, ji equals, if I multiply the j's first, that's minus 1. So I've got minus an I, so that's plus 1. So if ij times ji equals plus 1, then one of them must be minus the other. And it's not a problem. That's what leads to the meaning of 3-dimensionality. It leads to a cross product, which is characteristic of 3 but not higher dimensionalities. And you can't make it work if you've got more than 3 terms. So the 3-ness is explained by anti-commutativity. It's the same thing. It's not the primary cause of 3-dimensionality. It's simply a result of the fact that it's anti-commutative. So the 3-dimensionality isn't 3 dimensions, it's anti-commutative. That's where it comes from. And we can't force another axis onto this We can't also have, say, an L or an M axis. We can't do it because we cannot make our mathematics work if we do. Well, we can do it in a special way, but only in that way. And I always like to think anti-commutative things kind of know about each other, commutative things don't. So I and J know that they're anti-commutative with each other, but if there's something else, say A or B, multiplied by them, they have no idea that they're multiplied by I or J. The only way anything knows that it's like something else is by being anti-commutative with it. It's a very peculiar thing. Commutative things have no idea that they're being multiplied by something else. That's what makes them commutative. Now, quaternions are one of the 4 division algebras. We've already had 2 of them, the real numbers and the complex numbers. And there is one further one, the octonions, with 7 imaginary components. And this is the only way we could ever extend to higher dimensions. But these are anti-associative. For example, A times BC is not the same as AB times C. And even then we can't make it 9, we can only make it 7. There's no further way you can go on. And the dimensionality of space is characteristic of a non-conserved quantity. The dimensions are the same. They're like each other. They're similar to each other. They have an affine structure and rotation symmetry in the dimensions. This can only exist for 3 unless the system's anti-associative. So there's no extension of space as we know it to 9 dimensions. The only thing you can do is embed space into something else. If you create extra dimensions, they're not like those of space. We could call them something else. We don't need to call them space at all. And of course, division algebra is crucial for physical purposes where we've got measurement and counting. We need to have the proper mathematical processes. However, quaternions are the only pure 3-dimensional system in the sense that they only produce each other, they don't produce something else when they multiply by each other. Space isn't like that. Space is not pure 3-dimensional. We talk about 3-dimensionality of space. It's an aspect of space, but space isn't truly pure 3 dimensions, as you'll see. We go back to Hamilton to find out why. Because Hamilton, sorry, I didn't want to do that, early on, took a product of complex numbers and quaternions, which we can do because the complex numbers are commutative. So we can multiply them by anything, they don't know they're being multiplied.
Anti-space is not 6-dimensional because they're non-nilpotent?
So can we come up to that? Because, can I just go through and answer questions at the end? Yeah. We'll show all that as we go on. So we've got a base set of these 5 objects now, and multiplying everything out, we generate terms like this, complexified quaternions. And we will soon also write this, upright world. There'll be a reason for that. Now if I multiply these complexified quaternions out, the thing I get is not another one of its kind, but I times it. So that times that doesn't equal that, it equals I times it. That extra I spoils it from being a perfect, simple symmetry. And if I now write them in this form, we see that I times j doesn't equal k, equals let complex I times k. And now these are anti-commutative, and they're 3-dimensional, but they're not a pure 3-dimensionality because we've doubled our 3 dimensions. We've got another set of 3 dimensions which are complex versions of these. And they're all part of the multiplication process. Now these terms, the reason why I've written them in bold upright, is because we can now identify them as the Clifford algebra, the units of the Clifford algebra of 3-dimensional space. These are the vector units. Isomorphic to Pauli matrices, and I call them vector units. These are the true algebra of 3-dimensional space, but you can see they're no longer pure 3 dimensions. They're mixed up with this complexity. The products of these things aren't vector units, but pseudo-vectors. We call these pseudo-vectors. which are mathematically the same as quaternions. And we got yet another complication in that the triple product, and it is a triple product, is a pseudo-scalar. It's just I. And this pseudo-vector is typically area, angular momentum, pseudo-scalar volume. And so once we bring in space, we haven't got pure three-dimensionality, we've got something extra. It's more complicated. We're required to use a set of eight basic units: vectors, pseudo-vectors, pseudo-scalars and scalars. And if we include plus or minus, that becomes 16. And so this has to be taken into account when we're discussing the properties of space. So we explain how complex variables like time can be absorbed into. We were talking about this four-vector business, the four-dimensionality of space-time. We'll say more about that later. So if we take a complexified version of these, we naturally produce these four-vector units. If I take this as the 4 units of quaternions and complexify them, then I get that, and I also get this, which is like the 4-vector thing that we see in relativity. And even though the I term here is volume rather than time, because all I terms are commutative, it doesn't really matter. We can still absorb an extra I into the structure. So the existence of a complexified quaternion system, so we've got a complexified quaternion system for explaining space. But is there any role for pure quaternions, because they're the only pure three-dimensionality? And what I say is that you've only got to mention the word quaternion in certain circles, and there's fire and brimstone emerges from people's mouths. We've had 150 years of incredibly vituperative anti-quaternion propaganda, even though this is only pure mathematics. It's absurd, but we've been stuck with it. And even if you say, well, you know, if you can't explain space unless you understand quaternions, they say, well, all right, but nobody ever uses quaternions as quaternions. They're only a sort of shadowy thing. They've never found a physical role of their own. And in Hamilton's centenary in 2005, there was a well-known Nobel Prize winner going on in exactly that vein of saying that quaternions are no use in themselves, even though they led to better things.
Who was that?
Murray Gell-Mann.
Thanks.
So there's no doubt the quaternion system underpins the three-dimensional properties of space. And even better than just explaining space in 3 dimensions, it also explains spin, and it brings the space-time connection together as well. All of those things were done by quaternions before, mathematically, not physically, mathematically before they were done at all. And they could have been done from quaternions directly if people had known about it at the time. And it would seem strange if such a perfect system only has an indirect manifestation. So the question is, do they have any more direct manifestation in physics? And this is where I'm going to go to something I've talked about many times, and that's vital to everything I've ever done. And this is a Klein-4 parameter group. And the basis of this is that nature has a zero totality. And it's at the fundamental level, this is a symmetry between space-time, mass and charge. And the structure is that of the Klein-4 or dihedral 2 group, which is, among many other things, the group of rotations of the rectangle. It's a very fundamental group. And I was talking about this recently, and it's really only this. Once you've passed the sheer duality, this is the next step up, essentially. And strikingly, it's full of manifestations of three-dimensionality and anti-cumulativity as well. Even though it's a group of order 4, we've got lots of 3s in it, as we'll see.
What do you mean it's full of manifestations of anti-commutativity?
Well, here.
I mean, the group itself is commutative.
Yeah, well, you see these 3 across there, 3 properties. We'll see that.
We're talking about the Klein-4 group, right?
Yeah, you can. The way this group is, not just any Klein-4 group, but this Klein-4 group.
Well, but the Klein-4 group itself is commutative.
Yes, but I'm saying within it, within this structure of this Klein-4 group, not the Klein-4 group, this Klein-4 group.
Well, I mean, it's
And
it's related to the quaternions, which are not,
yes.
but the group itself, the Klein-4 group itself. is-
Yeah, I'm saying it's forward
So I
manifestations
think you're
within it.
saying, you know, it unfolds into the quaternions when
yeah.
you add signs.
Yes, that's what I'm saying. Yeah. See, the three properties alone tell you. This is a drawing that Vanessa did for me of the structure. I wanted her to connect these things together in such a way as you could see immediately all the symmetries. And you can see that some of them are about commutativity and anti-commutativity, the last property there. And I've also often represented it this way, and you can see immediately that this is a three-dimensionality. We've got three properties, so we can represent them plus and minus x, y, and z, and immediately you can represent that in lots of different interesting ways. You can use three colours, for example, which can map onto spatial dimensions. You can use actual spatial dimensions, or you can use spatial figures like tetrahedron. So there is, within this group, there's a three-dimensionality within the way this group unfolds. Now, both the set of parameters and consequent, as well as that, we can actually get these particular algebras for these components of the group. And the three of them are obvious. Mass is scalar, time is pseudo-scalar, the way we normally use it, and space is vector. We've got those three already. The one that we haven't got automatically is this one, the charge, the quaternion, or pseudo-vector. And we'll talk more about this.
Can you go back to the previous slide on the screen?
Yeah, I don't want
Okay, thank you.
I want to press on if I may, because I've got a lot to say. The least familiar one is charge, and it's not obvious. That one isn't obvious like the other three. That one fills an ontological gap, because you have to say where is the stage in between the vectors and the pseudo-scalars. And the reason is this: the concept of charge has only been slowly extended to incorporate strong and weak interactions. Originally it was only electric charge. And I can remember talking about charge 30 and 40 years ago, and people not understanding what I meant by this. And even so, even perhaps 20 years ago, well certainly only in the last 20 years, have people actually referred to the sources of strong and weak interactions along with electric interactions as charge. Even so, it's equivocal. This is Wikipedia here. Various charge quantum numbers have been introduced by theories of particle physics. These include the charge of the Standard Model. So they say the color charge of quarks generates the SU3 symmetry of quantum chromodynamics. Weak isospin, weak is the local symmetry and all that. Electric charge for electron. So they kind of got an idea that charge is responsible for the three interactions. But the way they do it is equivocal. It's like sort of, that's just a convenient wording. There is no physical connection between these. And the article also says in gravitation charges are eigenvalues of the energy momentum tensor corresponding to physical mass. So the basic...
The quaternion algebra, not your algebra.
I've not got onto that.
No, well, but this right here, the algebra.
No, that's them, that's not me. This is Wikipedia.
Oh, that's what I want to clear.
Yeah, Wikipedia. The idea is that charge is the source of the four non-interactions. However, there's still that there is some common structure. It's never explicitly stated. It's the sort of, well, we just call a charge something that does this. And the charge concept is only introduced in roundabout ways and seems confused. Its lack of brevity doesn't mention the coupling constants for the three interactions, which are crucial to understanding what charge is. Those three non-gravitational interactions have a coupling constant, and those coupling constants behave in similar ways. There is something very similar between them. And so why is this? The simple answer is that the four non-interactions are based on different symmetry groups, and also the differences between gravity and the other three. And you might consider, well, how on earth can we get beyond that? But there are clues that we can get beyond it. Because whatever extra complication manifesting, all four forces have a Coulomb, or inverse square law component. And in the case of gravity, it's attractive for light particles. In the case of the other three, it's repulsive for light particles. This is what we call the coupling constant. It determines the quantity of interaction. There also appears to be an energy regime where the difference between the three gauge forces, that's the non-gravitational forces, disappear and the constants become equal. And this seems to be close to the Planck mass, which would link the gravitation with gauge values. I also think that there seems to be evidence that the character of the gauge forces becomes purely Coulombic. They lose their special characteristics when you get to a high energy. It's only in a lower energy regime that would be apparent. So what we need to do is set up a working hypothesis, but not for long. I don't believe in big hypotheses. I believe in hypotheses that within a few lines will lead to the next stage, in which the gauge forces stem from a three-component or dimensional quantity charge, which is imaginary and therefore quaternionic. And so that explains the difference in sign between the imaginary charges and real masses. So they will have opposite forces. Kant showed in the 18th century inverse square forces are direct manifestations of the three-dimensionality of space, and the manifestations of the symmetry surrounding a point source. So we would expect to see that. And so, if we like to begin, we will say we can set up a quaternion charge mass structure which is opposite in every characteristic to the space-time structure. Now, I do have reservations about space-time, but I'll come up to those later. The total structure has interesting parallels to an octonion. It's like a broken octonion, and I've actually represented it like an octonion with a lot of success. The anti-associative aspect seems to be those that don't have any physical manifestations. So that's a diagrammatic representation. So, okay, if we say the quaternionic structure would explain the Coulomb aspect, which is part of all these forces, it doesn't explain the extra terms which make them different. And what I want to show now is that you can't do that directly. You've got to do that by interacting two separate three-dimensionalities. So you've got to have two three-dimensionalities to explain why you have these strange manifestations of the gauge forces, other than the straightforward Coulomb one. And this interaction between two spaces, don't mean interaction in the sense of force, explains why we have any point particles at all. I want to mention very quickly that the application of the three-dimensional structure to these things explains what suggests that only three-dimensional concepts, structures can be discrete. If it's discrete, then it's three-dimensional. If it's three-dimensional, it's discrete. It's the same thing. Discreteness isn't something that applies except in three-dimensional objects. If this group is what physics is about, then the continuous things like mass and time have to be separated from the discrete things, but those discrete things have got this three-dimensional or anti-commutative structure. And the discrete charge is obvious, it's a conserved quantity. That space is more subtle because it's non-conserved and so has no fixed units. But I've explained in previous talks why it's necessary for space to be an observable quantity and to explain Zeno's paradoxes. And in fact, you couldn't possibly imagine a non-dimensional quantity as discrete. If it doesn't have dimensions, how are you going to divide it up? You just can't. You've got to have zeros or crossover points. A discrete point requires three dimensions. You can't actually create a point unless you've got three dimensions. You can't create a point in one dimension. It's meaningless. And physics has a natural relation between anti-commutativity and discreteness. I'll leave out the real-life structure. Okay, now I want to write down the algebras that we've assumed are true for these quantities. This one we know is true. This is the vector algebra with all its bits. This is the vector bit, pseudo-vector, pseudo-scalar, scalar. That's another way of writing it. Just write those as quaternions instead of pseudo-vectors. Charge. Actually, that's not correct. Just be. No, that is. Those eyes there should be bold. I'm sorry, they should be bold upright.
Yeah, that could be. They all should be upright.
These three should be upright.
And in the top line?
That's correct. That's correct. These should be upright. These II, IJ, IK. Yeah, that's how they should
The
be.
red eyes, JK should be upright. Right?
Yeah, the red one should be upright. Okay. Now, what I hope to show here is that these three are subalgebras of this, or equivalent to subalgebras of this. They're not actually subalgebras because they don't belong to space, they're something else. But they've got the same algebras as if they were subalgebras of this one. See, these three subalgebras here, that's 1, 2, 3, 1, sorry, 1, that's better, 2, 3. So the other three quantities are subalgebras of the first. I think I've got it right on there. No, I haven't actually. Now, these shouldn't be upright like those. These should be upright. So these three are subalgebras, and what one can do is put these in a combination all together, and we would get the same algebra as we got space. They're not only subalgebras, but put together, bundled together, they will give the same algebra as space. Let's see if I've got that one correct. I've got that one correct. Yeah, this one's correct. This is space, and this is the combination of the other three. Exactly the same algebra structure. Now, if what I say about the Klein-Ford group is correct, then there isn't any physics. That's not in that. That's what physics is all about. How do I put those two together to get the whole of physics? Well, it becomes effectively a double space. Because one space is space, and one space is everything else. Time, mass, charge, everything else. How do we combine them? Well, we can combine the algebras. That's how we combine the algebras. If I multiplied everything out every way you could possibly do, that's what I would get. And the thing is that we end up with 64 terms.
And that's a point. That whole algebra.
I'll explain it to a point. Sorry, can I go back? Forward. That one there. See, these are the vectors, these are the quaternions, but these are all the combinations. These are pseudo-vectors, and these are the imaginary quaternions, and so forth. And this is the pseudo-scalar. And you've got plus and minus of them, and you've got all of these. What I want you to notice is these groups of 5. You see that in principle they all look similar. They've got similar structure. That's crucial for this. They've all got a similar structure. We could use 2 spaces as base units. We don't need to use what we've done, the 8 that we've used. We could use. If I multiplied all these out, I would get that 64 as well. I'd get that as well. So we could use those 2 spaces. This one bundled together and this one separate. Now, you don't need to know all the elements in a group to specify it. All you need to know is the generators. The generators are just any number of units in that group which will generate the entire group by multiplication. And there's always a minimum number of generators for any finite group. For this one, it's 5. It's not 6. So this is the minimum number of generators. That's 6 generators. Now we can do it with 5. And in fact, we can do it with any of these 5s. Any of these 5s will generate the group. So to specify the whole group, I only need to specify one of these lines. Just that one, for example. Like that. That will generate the entire group. This doesn't exhaust the options. We could reorganise the 60 units as 12 sets of 5 generators in at least 64 ways. That's not a unique splitting. I could do it in lots of different ways. We could use any arbitrary symbols, but the key thing is that these generators always have the same structure. This is absolutely crucial. If I look at this one here, I see that 3 of them, these blue ones here, are attached to the same object. So this structure here, which is basically that of space as we know it, is unbroken. The symmetry is still preserved, even in these generators. However, if I look at the other object, the red ones, the symmetry of this one is broken because the red ones are connected to something different. So the minimum generators, the minimum bundling together of this stuff to get the maximal information is in fact a broken symmetry. 5 always breaks symmetry. This is one way you can do it. This is physically how we actually do it. I take one of these objects from charge, stick it onto time, one onto space, that one, and one onto mass, and I get that. And this gives me the 5 generators. You've got to break the symmetry of one of the 2 spaces. And naturally, the one we break is the one we don't observe. Space is a non-conserved quantity, so we want to preserve that rotational symmetry. We want the 3 units to be the same sort of thing always. But we're not bothered about this one because we don't observe it. And the one we break is that of charge. We can show that the 5 generators, among other things, leads to the broken symmetry between 3 charges. This is the thing that's troubled us forever before this. Why have those forces got different properties? It's because the symmetry between them is broken. This one here, we can eventually show, and I can do this, we show that the SU2 structure of the weak interaction comes from this. The fact that it's connected to a pseudo-scalar there, not I. The SU3 structure of the strong interaction comes from the fact that it's connected to a vector quantity, ijk, blue. And the electric stays as a scalar, so it ends up with a U1 symmetry. And so we can see that the units of the second space now adopt the characteristics of the mathematical objects they're connected to. Also, in addition to this, so we can look at it from the point of view of the red things, which are the charges, but we can look at it from the point of view of these things, which are the other parameters. And this one creates a new parameter, which we now call energy. If we connect time with this K, it creates a new quantity, which we call energy. This one creates a new quantity, which we call momentum, and this one creates the rest class new quantity. And those letters E, P, and M are just scalar values, just made up. They don't have any algebraic significance other than that. So these scalar values, we can attach any scalar value to these units. It's completely arbitrary what scalar value it has in this group structure. And then we get an object like that. And this is simply packaging the whole information into one package. And if we multiply that by itself, we can immediately identify this as Einstein's relativistic energy equation. Because we drop the C's from the M and the P for convenience. And if we then choose to quantize that equation in a conventional way, we will get the Dirac equation. I don't wish to go into detail about that today, but we will get the Dirac equation. What I do want to point out is that if we include all the possible sign variations for E and P, we get 4 terms, 4 terms for E, 4 terms for P, and 4 terms for these differentials in this Dirac equation. And this we can call the Dirac wave function. And this is a special form of the Dirac equation. It's the nilpotent form because this object is a square root of 0, and the wave function is a square root of 0 as well. And if I were to do a parity transformation on that, let's say that, I would get that. If I did a time reversal, I would get that. If I did a charge conjugation, I would get that. And so we can see that the other three terms, other than the first term, are the P, T and C transformations that could be done to that first term. So if you like, this is the particle, and these are the states in which it could transform by those transformations. And if we square this to 0, and this is a wave function, then this is immediately Pauli exclusion because we can't have two identical wave functions because they were 0. So fermions appear to be point-like objects with norm 0. They square to 0. And if you create an object like that squaring to 0, it's the only way, in my view, of defining a point in space. You can't actually define a point in space using pure geometry, because space simply runs away from you. It's translation, symmetric, rotate. You can't specify anything in it. So we can define. Where are we? That's right. We can define a point as an interaction between two spaces. So it's like a crossover between two spaces. You've got the space we understand and the space we can't see, which is the other one, which is a crossover. And in fact, the Schrödinger solution of the Dirac equation for the equation of motion of the electron gives us a point-like object switching between two things, between its own state and a vacuum state. And it calls it a Bavarian. And the fermion spends its whole life doing that, and that's the reason why it has spin half, because it's only half time in this space and half time in the other. So we can't define a point or the space in which, without defining another space in which with which it interacts, produces totality 0. We're back to our totality 0. And one will appear distorted with respect to the other, but in fact both contain the same information. And we could extract it from either. Now, if I return to Pauli exclusion here, we can imagine creating a particle with everything that it could be in this form. This is just a generic form for a particle. And then we're forced to actually zero the universe. We create the particle out of nothing, and we're forced to maintain the 0, so we have to have this as the rest of the universe. The rest of the universe is a kind of mirror image which zeroes it. And that's what we call vacuum. And both superposition combination states of vacuum and fermion become 0. So the whole left by creating the particle from nothing is the rest of the universe needed to create that particle. So it sees, any particle will see the rest of the universe as a kind of mirror image of itself, which will zero it. So vacuum tells us where the other space is, insofar as there is anywhere. Its inaccessibility is demonstrated by the chirality between matter and antimatter. We only see matter because antimatter is in the other space. We only see positive energy because negative energy is in the other space. We only see forward direction time because the negative direction time is in the other space. So if we get a structure like that, even though this is supposed to be for a fermion, say an electron, we still have two states with minus e, and two minus dark time directions. And yet only these are observed. That's because the others are not in the observable space, they're in the vacuum space. But there's as much of them as there is of this. So it's the one in which charge is conjugated and time reversed simultaneously. So if you conjugate time in this, if you reverse time, you conjugate charge. That's why Dirac said that negative energy can't conjugate into charge, the opposite charge. The nilpotent structure, nilpotent because it squares to 0, incorporates both on an equal basis. I'm not going to say anything about Feynman path integral at the moment. So the non-local aspect is defined by continuous vacuum. This continuous vacuum with its negative energy appears to be in fact associated with gravity, because gravity has those exact characteristics. And that one can develop a gravity theory based on that. And this is in some sense an inertial term reposing the gravity, as it were. We can use these operators to partition the continuous vacuum state, or the inertia which opposes this, into discrete components with a dimensional structure, which then become the weak, strong electric components of vacuum. And what you can do here is multiply this by k times that, and it doesn't change this at all. Mathematically it doesn't change it. This is an idempotent, it multiplies to itself, and it doesn't change this in any way. So it acts like a vacuum operator. But it's not the whole vacuum, it's just this. If we multiplied it by the whole vacuum, it would disappear. But if we multiply it by one component of vacuum, then we can see a particular state. We can do the same with I and J. Another thing is that every alternate bracket, we can switch signs. If I do this, the alternate brackets, you can do a clever trick here, because you can multiply the alternate brackets, this one here, by k on each side, in which case you change the sign of that, and the k's disappear. And so we have, that's the same, that becomes minus, that's the same, the next one becomes minus, and so forth. And in fact, we're using the T, P and C transformations for the alternate brackets. And when we combine these with the unchanged bracket, we get 3 different types of bosonic structure. So T and C transformations occur in vacuum space because they concern vacuum space quantities, time and charge we said, are in vacuum space. They're not in our space. The P transformation concerns the real space quantity and leads to a positive energy state. But we could, in fact, transform both of those and it would be equivalent to a P transformation. So we could do that in our space as well. And the fact that we can do it in both spaces is the reason why there is an overlap with this Zittauer-Wegung, and that's given by the mass of the particle. So we see how that happens there. So the vacuum space, these charges have also PCT operators, dimensions of vacuum space, generators of the 3 additional terms in the Dirac wave function, creation operators converting fermions to 3 types of boson. They do all of that. We can also take this object to convey the angular momentum information about a particular state. And so, we can see that units also say something about conservation laws and the direction and magnitude of this quantity. But you can get angular momentum. This is a classic case of how you can get the same information from the 2 spaces. You can get the angular momentum information either directly from P, which is the angular momentum, directly, or you can get it from K, I and J. So it's exactly the same information. And what I want to show you is that you can do Pauli exclusion by either saying that this thing squares to 0, or you can take antisymmetric wave functions, and when you do that you end up with this. And all that, what that finally says is that the only difference between 2 fermions that can ever be distinguished is that they have different instantaneous directions of spin. It's a remarkable thing. I couldn't believe this when I first got it. But that's what it means. It means that all that distinguishes 2 fermions is their instantaneous direction of the spin. Not even the magnitude, that doesn't matter at all. It's just the direction. But what I'm going to do is show you this. So I can use real space, and that gives me my angular momentum because I've got 3 directions. That gives me my spin direction. Or I can use vacuum space, which is the red thing. So I couldn't get the red on this diagram at the time. And that shows me the same information. So these spaces are truly dual. And the reason why they do is because they total zero.
So would they, if they're dual, would their directions be moving in the same or opposite? The spin directions?
Well, the spin direction will be the same, but in
Oh,
fact
okay.
it would be opposite.
Oh, okay, okay.
Yeah.
Correlate.
But it would look the same because it's the same direction. And this is to come back to what Anton was talking about here. One of the remarkable aspects shows that the four-dimensional connection in special relativity isn't four-dimensional at all. There's no four-dimensional connection. That is nonsense. If we look at it now, this is special relativity, energy, momentum, mass, and we can do it time, space, and proper time if you want. But if you look at it, you've got blue things which are vector, you've got the I thing which is pseudo-scalar. Vector and pseudo-scalar, 4-vector. But in fact, that isn't true because we've got also another term interpolated, the K and the I, which separate them. And in fact, the connection is three-dimensional because that's the time, that's the space, and that's the proper time. So, I mean, the equations are correct, but the interpretation that they're actually four-dimensionality isn't true at all. There's no four-dimensionality there at all. It's an apparent four-dimensionality if you take the scalar product. But if you're looking at the object itself, there's no four-dimensionality. It's too complicated to be described as four-dimensionality. If it was four-dimensional, there wouldn't be any red things there. If there was no red things there, it would be four-dimensional. But the red things are interpolated. And even in the very conventional way of doing it, you get gamma naught there, gamma 1, gamma 2, gamma 3. You get different objects. And again, space-time connection isn't privileged over those with mass and charge. There's as much connection with mass and charge as between space and time. Thank you. This is something I like. The fact that you can make an immediate analogy with the case of three static forces in equilibrium. So if you've got three static forces in equilibrium, you can write them as a sort of nilpotent. If you go around a 3, 4, 5 triangle and end up that way you started, you can write that as a nilpotent. And so you can write that as the vacuum space version if you want. And if you have two forces adding up to a resultant, if you like, you do that in ordinary space. If you have two forces, and then the force that would cancel those, you do that in vacuum space. Because that's because you need the zeroing of the structure. Oh, I can't move that. I'm not moving it.
What do you want to do?
No.
Full screen.
Yeah, no, that one.
Right,
No, I have to move it over here. I don't know what I'm doing there. From current slide.
Somebody gone more.
I'm not going to go into huge details about that. You can do the same with particle structures. I'm going to go through this very quickly. I explained how baryons worked by using this momentum operator to separate three
I think
components.
you switched it off.
I think it will. Yeah. Thank you. So I can do this and actually get perfectly good explanations, get good calculations and the rest. And this is how I can do a baryon structure. And I don't know anybody else who's found another way of doing baryon structure. And what I'm saying is that I'm doing this through the ordinary space because momentum is the same, is basically connected with ordinary space. But I can do it through charges, and that's more difficult, but I can do these structures here, which I can do through the charges. So anything that's done through space has also got a reflected version in charge, but I will go past all that because it's quite complicated and I shall leave that. What I'm going to say is we've seen three components of charges, the three-dimensionality separate from that space, but acting against it to produce zero totality. And other three-dimensionalities emerge from either one or the other of these. 3 quarks in a baryon, well that's ordinary space, though you can do it using charge, or therefore vacuum space. 3 generations of fundamental particles, I can't understand why this is an issue anymore. It's still obvious why it exists. So, according to the Dirac equation, massless fermions would be called left-handed. So the measure of a fermion is a measure of how much right it is. The mass of a fermion, that should say. How much right-handed. The mass of a fermion, not the measure of a fermion. Higher mass fermions are more right-handed than lower mass ones. And we can see that the second and third generations simply produce step functions in right-handedness. They just violate parity and then turn for inversal to give a step function in right-handedness. So it's just CPT, which we've already shown where that comes from. And there you can have a conserved three-dimensional quantity as rotate, a non-conserved has rotation symmetry like space. A non-conserved one looks like charge with a broken symmetry. Now, a bit of entertainment at the end. I've done this before, but I'm going to do it again. Physics and mathematics, I think, are linked at a very deep level. One doesn't simply use the other, that's nonsense. They both exhibit the same patterns and structures. So let's start with a real scale unit 1. This is a bit of entertainment. How do we conjugate this number to obtain zero totality? Let's say we do it through using a physical structure like mass. Uses scalar real numbers like 1. It's a conserved real and a non-dimensional quantity. So let's try and find a conjugate by non-conserved imaginary dimension. Right. In mathematics and physics, non-conservation is expressed by differentiation. E is a number that arises only out of differentiation. So that's non-conservation, if you like. I is the basis of imaginary numbers, no problem there. And pi is a number that arises only out of three-dimensionality. Spherical symmetry. So each di pi gives a number which is conjugate to 1, because we've done all those 3 things. So I say these transformations are very similar to TCP or PTC transformations. Okay, thank you.
You had a question.
There was a slide a little while back about Feynman path integral.
Oh yes,
How you're thinking.
I
didn't quite understand
well,
what you were saying.
I'm guessing.
Can you bring the slide back?
I've been reading Feynman's thesis and the description of it and so forth.
So I understood Feynman's motivation partly to be that he wanted to look at a Lagrangian version of quantum mechanics rather than a Hamiltonian version.
I don't think that's the case.
And then he discovered, indeed, a Lagrangian version of quantum mechanics.
Yeah, I don't think that's the case. I think when he was trying to do one in which he could get plus and minus t at the same time, and plus and minus e at the same time.
Plus or minus
E and t at the same time.
You
know, he reversed time. He wanted to. It was part of the Wheeler-Feynman mechanism for explaining why you only got advanced, retarded solutions and not advanced solutions. And he wanted to see why the time, why you only got one of those. And so he wanted a mechanism of quantum mechanics which would include both. And he couldn't get it using a Hamiltonian method at the time. He could only get it using.
So that was an extra reason for looking at the for going away from the Hamiltonian.
Yeah,
method.
I think so. Yeah.
But the thing that he always emphasized was that he had essentially a least action principle for quantum mechanics by a stationary phase, right?
No, I mean, that's a great thing to be able to do. But I think you could actually get more out of the Hamiltonian methods now.
Yeah.
Now that you can do plus and minus e, plus and minus t straight all at the same time. And so you're not so constrained as having to do it that way. It's a choice, and it's a good choice, but it's not the only choice.
Where's that slide where you mentioned?
I don't know.
I wanted to read it again.
Well, why not just take the copy of the presentation?
It's all right. You don't have to worry about it now.
Yeah.
The other thing was Kant. Could you flip back to that slide with Kant on it?
Yeah, as far as I know, he's the first person to say this.
You were right next to the slide that had Kant.
Was I? That's after this, I think.
Really?
There we
Yeah, all right. I mean, I tend to think of inverse square law and three-dimensionality as related because when you integrate, you know,
Yeah.
a 1 over r squared, you can pick up point charges from, but what did Kant do?
I think he showed, you know, that if you had any other dimensionality, you wouldn't get an inverse square law.
Does it give them?
Well, but you say that Kant, I mean, you know, mathematical physicists at that time certainly were interrelating inverse square forces and the three-dimensionality.
They were.
Kant
I think
but I didn't know that Kant did anything mathematical. That's what I
maybe
was.
it wasn't mathematical. Maybe it was an argument that they hadn't made explicitly that he did. I've forgotten now the details.
So he had some philosophical
Yeah,
argument
I think so.
relating inverse square and three-dimensionality.
I believe so,
That would be
yes.
interesting to know what he said.
Yeah, well, I can give you the reference. I've got it somewhere.
Yeah.
Okay.
You know.
Who, Mr. Chairman?
No, you know.
No, go ahead.
Two points. The first, for what I understood, because the first one is an historical remark. For instance, when you said about fermions that each particle mirrors the rest of the universe,
Yeah.
that's Leibniz notion of a movement.
Yeah.
And probably Leibniz didn't have, no, as a matter of fact, he didn't have all the algebraic maths to analyze. So it would be interesting to see how this works in his way. Just to give an example, he has this notion of of a complete concept. For instance, he says the complete concept of Adam contains the complete history of all mankind. So all the universe is mirrored in that place. So, but that's just a matter of. So it would be an interesting way of reading.
But does he go to totality zero? Does he?
I don't know.
Yeah.
But I think it could be.
You can do quantum mechanics. You can say that about quantum mechanics. But if you've got the vacuum,
read Leibniz in this perspective.
one might be able to do.
If there are hints. No, and the second point, it's kind of when you said of the talked about of the fact that maths and physics are very strictly connected, and actually they deal with the same structure.
Yes.
And my impression, purely qualitative impression, is like you took the entire construction of contemporary physics and sort of X-raying it and seeing the hidden structure, the algebraic hidden structure.
That's my intention.
No, I mention this because there is something similar. I'll get to a point in my slides about language, which is like physics in this analogy, and the formal structure that language has, which is like maths, and they are strictly connected,
Right.
and not a kind of meta-linguistic description.
I understand what you're saying, yeah.
Yes.
So you're saying that's true for that as well? I can well believe that.
I think that...
Because these are they're both information systems, really. Yeah.
Yeah. Okay, thanks.
Okay, let's give Peter another thank you. For the interest in his talk, maybe we could persuade Lou to give us some time of these double slots to ask further questions.